Okay. Voice are good. Everyone hears me. Great. Hello. Welcome back to quantum mechanics. Today I'll be presenting about ultimately what is Heisenberg's uncertainty principle. Oh, to start, let's just remind ourselves that like the basics math, I guess. Or it's stream. It's only two of us. I planned it for my plan to be most people in 247. So we're inside of a Hilbert space, and that essentially means that we have some sort of linear operator from the Hilbert space to itself, where t is self-adjoint, and let's say if you apply t is equal to t star, which is equal to t's transpose, the conjugate of its transpose, right? That's how you transpose. Let's stick to this notation. We'd also love to say that like we have some state vector, let's call it psi, which is just really a linear combination of, well, 1 second. Let's put it in bracket notation. It's just a linear combination of every single ai and lambda I. That's how Ivan writes it. So you have like a probability, essentially, of something happening, and the observation itself. But for our purposes, we're going to treat lambda I as eigenvectors. So you have t psi, or well, not t psi. How should I say it? T for any vector. Let's call it the I is equal to. This is a really bad slot. Uh-oh, I'm already messing up the board. We'll get to that later. Essentially, you're saying if you have a vector, you can split it into its probability and what the thing is, whatever we want it to happen. Please keep in your mind that we're going to treat it as some dice. We're going to use this dice analogy a lot, where a dice has a lot of faces, and you can have any arrangement of numbers. And of course, since we're messing with probability, we kind of want the usual like probabilistic tools. And number one, we want to define the average or the expected value. So let's call it E of lambda. No, already messing with this. Am I? 1 second. Yes, let's call it E of lambda. And well, this is just, how should I say this? Let's say just by definition, and we can get an intuitive feel later. It's the sum for all lambdas that are relevant of lambda, the probability of each lambda happening. And secondly, you also want like standard deviation, or in this case, variance. So number two, we have sigma squared. Ivan doesn't write this down, but I'm going to write this down as some, or maybe I should write it down later. We'll see what pops up. Let's leave some space. Equal to expected value. That's not E. Of state observation minus the expected value of the observation of all observations squared. Right. Let's define it this way. And we have an expected value here. So this is essentially saying take any observation subtracted by the mean of what you'd expect for the entire state, and then you square that and feed it back into this function. We can plug this E of lambda back in here, and we're going to get an equivalent expression. So we'd get the sum relevant lambdas of lambda minus E lambda squared times the probability of each event. Right. This is just you plugged here into here, and you factored out the sigma notation and wrote it down this way. Finally, this is sort of like a black box. I don't know if we've seen this or not, but we're going to define a commutator relation. So for all, let's call this just AB. For any two observations or operators AB, we're going to define this is equal to AB minus BA. Specifically, to get some intuition later, this is going to be equal somehow to some K times I, where K is inside our complex. Right. This is the basic setup or the overview. So we want to hit 3 targets. Yeah?
The K times I thing is like a special case.
Okay.
Special case of yeah. So in general, it's not some constant multiple of the identity.
Right.
It would be nicer.
And a lot of question marks. We're gonna see a case where this is equal to this, where K is just some constant inside your complexes. For now, let's focus on these two. To define expected value, we're gonna need this. This is just probability of each event happening. Oh, I think we saw this last time where we went over some other like particle in a box where we define P of lambda as, of your, yeah, so this is just norm of your squared. But importantly, this is I, just that, or more in the center. I'm going off by the book here, but what this is essentially saying is the probability to get any one event, so say like the chances of rolling a die and getting a 1 is the sum of the associated probabilities of you getting a 1 on any individual face. There could be many faces. In fact, there are infinite faces in this die, and maybe there are infinite 1s. So if I wanted to get any set of 1s, I add the probabilities of every single of the chance of getting every single 1, or how should I say this, of getting a 1 on any side of the dice, essentially. You could also think of this, if you go back to our function, the probability of getting anything that we want is if you knock out all the other eigenvectors of the stuff we don't want. And so you're kind of just left with this, and that's why you're adding only the eigenvalues of, or any of the, this is an eigenvalue, yeah, it's just any associated coefficient inside of complexes for the measurement that you want. So this is why it's the sum of many, and it's not necessarily just one. Now that we have some sort of probability, and then we can define the expected value and the variance, we want to bash it a bit with algebra to get something more manageable, because we'll see very soon that this is kind of unusable, and we're going to need something else in order to get any semblance towards Heisenberg's uncertainty. I'm going to make a claim. See if I've gone there yet. Right, I think I'm good. I'll just mention on the board that we wrote this down. These are orthogonal eigenvectors. So by definition, we've set these to be orthogonal eigenvectors, or orthonormal bases specifically. Orthogonal eigenvectors, same. You can get this because of spectral theorem. That's an important thing to say. Anything else? I think we are set. Yes, we are set. So this is the setup. I'm going to train this is the main board. We're going to add stuff onto here. Let's turn our attention over here. I'm going to make... yeah, I think we can see. Right. So I'm going to define something. Define this to be equal to the inner product of your state and the operator times the state. So this is sort of like observing the state, essentially. This is how we define this thing. And I claim that this is, well, let's just say it has some similarity or bears some semblance to the expected value. Right? Okay. The notation might be a bit strange because what I'm saying here is it's a generalized like probability of applying any measurement on psi when I'm really specifying to a specific like observation, specific eigenvector here. But just think about it as this is being equal to the average, essentially, average of making an observation. To do this, we're going to, let's see. Where are my notes? Yeah, you're the only one. Also, there's no one on the screen. Let's just double check. Dude, I just went over this. What happened? Right. We're gonna make a hazard substitution. So remember that when we define A, we specifically wanted to find eigenvectors. So like A applied to like AVI, let's write this way, it's equal to lambda VI. This is just to say that we're really interested in only the eigenvalues inside of A. So when we operate A on any like vector V, we want to get the eigenvalues. And so if we use this intuition, this is this thing, psi, will be equal to lambda times the sum of all lambda vi's. Let's put lambda here, vi's. Where we're trying to, this is just by definition here. We apply the vi, and we're trying to find the eigenvalues. We get this, but you could also break down psi itself into the sum of any just general like coefficient and then your eigenvectors. Ooh. Wait 1 second. For our purposes, yeah, but do we want to use bracket notation?
Up to you. You can use
Vi. It's gonna be a bit weird though, isn't it?
Yeah, just do this. First you have like different eigenvalues, and then you can make like say write all the lambda i's to be like vi instead for notation.
All right, just call it there.
Just call that more comfortable.
Lambda vi's.
No.
Lambda I, no?
No.
Huh?
Do it slowly. Keep the operator first and expand basis.
All right.
Keep the operator.
Expand basis. Let's split lambda. Oh no, let's split psi for now. And if you we define psi as a sum from AI. We define lambda I here, but we made a transition, so there's just this. And so we're gonna call all of these, yeah, change it to vi for now. This is equal to AI vi times a, and then the same. But for our research, call this aj vj, just to differentiate for now. And when you apply a to all of these, right? So we changed them. We changed we essentially expanded what psi was. I would call them ij just to be able to differentiate. Particularly when you apply a to this, you apply a to each individual one because it's linear. And we defined here previously that when you apply a to vi, we care about its eigenvalue, and so this is equal to so lambda j vj. Since it's linear, we're gonna take out something. We can take out first of all this. So let's take out some. These are i's, by the way. J. Let's take out a of ai. Please do note that we come from a mathematics background, so the second or the when I extract this will be the one that we have to extract in conjugate. So this is also equal to the sum of I j ai lambda j aj when both of these are in conjugate, and we are left with vi. Please note that this, by definition of how we defined our state vectors here, these are orthonormal and they're eigenvectors, and so for all I not equal to j, we can just, or first of all, we can, for notation wise, we can reduce this down to Kronecker delta. And we consider the case where only I is equal to j. And so this will be equal to right. Ooh. Hmm? Right. My bad. Sure. Well, j, and there is a j. yeah, J. We are. I am forgetting my basic linear algebra. We can merge
Also, like,
the conjugates.
harder.
Hmm?
Write harder so the color comes out.
Okay. Right. We can merge, right? Hold on. Am I forgetting basic linear algebra? Please, no. Sorry. J. Or, well, we could do the other thing. Oh, something went wrong. Hold on. Oh, no, I'm just looking. All right, Mirren, help. My brain's not clicking.
So,
Is that right? We want to condense using projecting.
okay, this should be a lambda.
Right.
And then, so these are all summing over j's,
Yeah.
and we know that something times the conjugate would be the norm squared, right? So this would be AI squared, and then lambda j, because from spectral theorem we have a self-adjoint operator, so the eigenvalues will all be real, right? So it would just be lambda j, and then this looks like something.
Pull your attention back to this. We can plug this in, and I think they can see. This is equal to lambda j, or well, still need a sum, right? JJ ice. Do we need to switch this to j, or is this fine being I?
Whatever. No. They have to be the same. Those eyes are both.
All right, let's call this j. Try clearly. Sum for all j's. P of y, some j's. Uh-oh. Why do I not get the sum? Let's call it j. All right, well, this we can forego this. Lambda p. Lambda. The summation. Why is the summation still there?
Yeah, you need this.
Lambdas. Right, because remember that there you might roll a like one on a die. Like a dice has more than one side with a one, and so you still need to add over all the possible like sides you can get.
Look at the formula and look at an average.
Dude, my brain is not working. I slept 2 hours. Yeah, but if you plug it in, you don't get a summation. Am I dumb?
Look at equation 1.
Yeah.
That's exactly what you have right now.
Sure. Right, and white square. So we have shown that this definition which we've had, let's see if you can see it. We've shown that this, and particularly this, we really care about this thing. This is essentially equivalent to our expected value or average. And so you can get the average of any observation, any operator A, by running this thing. And so, convinced? Convinced? Okay, great. We're gonna go here. This is also equal to a psi, and we're gonna write a side note here, which is just right. And now let's. So that's part one. Let's be sort of neat and let's try to get rid of. This eraser's really bad, or a whiteboard marker. I'm just gonna erase it with my hands, probably better. Right. So now we've done one, and we've got something really useful for one that we can use. We're gonna check this off. We want to engage now with two. So we want to get something from the the variance that is usable instead of just saying the expected value of something and the expected value, which is slightly confusing. I will make, honestly for worse, a pretty long logics jump. Let me just erase all of this first. My claim is, if you can pull up your knowledge on normal statistics, the variance of some observation A of psi is equal to the quantum version of saying the mean of your square of your means, mean of your squares subtracted by the square of your means. So normal probability, this is like saying, if I want to get the standard deviation of rolling a 1, it's or on any set of data, I take all the data, square each individual point, take an average, and subtract it by the square of the average. We want to show this also applies using like QM knowledge and more advanced math. The starting, I guess it is a pretty long logic jump. We want to turn our eyes back over here. We define variance as something inside of an average. So forget this exists. It's the average of something. And we're going to use this sort of terminology saying, if this is the average of something, we're going to call this entire thing like A. So this becomes our operator essentially, or this becomes some like operator T. And if we can call this an operator, then we can also plug this back into here. And so what we're going to do is we're going to plug all of this inside here. That's sort of a trust me. It's not too clear. I guess I'll have Ivan clarify it and then make sure all the edge cases are being applied well. But you're essentially converting this formula into this formula, and you're applying whatever's inside into whatever goes inside here. Yeah, I'll write it out. So we have standard deviation squared of A in state psi is equal to psi. I should put this in another color, but let's just write it like this for now. I think I just need to stick to one side because it makes it thicker. So note that this was equal to E of something. So I took this as the, I did not write everything I need to write on the board. Right? Expected value is equal to variance is equal to the expected value of something. Whatever that something was, I took this and I plugged it into this formula. This is the expected value, it's equal to this, when A which is whatever's inside of here. And that's what I did. It's not really rigorous, and so for now, this is just a trust me that the logic is as simple as that. Maybe you'll learn later. And so now this is just a bunch of bashing it with algebra until it works. So we're gonna first of all expand this, expand what's inside. Oh, right.
You want to write it in
QM form. This is why I said I wanted a different color. Lambda doesn't really work here. This is in bracket notation. And so we want the thing that's associated with lambda. We said that if lambda was our like observed probability, then the operator A is it's like a measurement. Then the act of observing it the act of observing it is A. And so the math version of this is A times any like orthonormal vector is equal to like lambda I vi. That's the math way of seeing it. The rhetorical way is just saying you have a measurement, and so you want to get it the way you observe it. And so we replace this by A. The expected value of lambda is the expected value or the average of A then. And then we can't write like E of A, so we resort back to our notation over here. It's this. And so this is, I don't know how to say it. It's just the quantum way of writing it. So this becomes here, A and psi. And because we want it to be mathematically rigorous, we multiply a scalar, since it's an average, it's the number of the complexes, by I. And square it.
Clear the first A there in the yeah, this one is not the same as the other.
No, this is an operator. Like think of this like a linear transformation. This entire thing is a scalar because it's an average. We define this to be like the average. This is just equal to like E of lambda, essentially. E of lambda. So this is like essentially an average. The average of you observing the state versus the act of observing the state inside of a weird math language. We're okay?
Yeah.
All right, let's proceed by just doing math. So we can square. Let's write it out. And make sure I don't make any silly mistakes. Expansion. FOIL. So you have lambda times first, inner, outer, last. You get AA times psi, because it's linear, squared psi. And then you have minus 2. We're going to put our scalar first. So A psi plus this times this is squared, so you have this psi. Good. Okay. And now we're gonna, well, let's break it. Let's use bilinearity first. So since it's bilinear, we can chunk apart these components and be okay with it. Oops. I don't need this anymore. This was a scalar, and we can pull it out. We're fine with pulling it out. And then we have this. Right. We see some interesting things. Firstly, can we reduce this? And what does this reduce to?
Did we assume that psi is normalized?
Yes. Psi is normalized here. This is what we meant. Psi is normalized here.
So later product there.
Voila. This becomes 1. So this is a check. Can we say anything about this? I'll just highlight it so it becomes very clear what I'm pointing at.
What we defined.
Great. We define this as just the average, essentially. And so this is equal to -2 square, because we have 2 terms, and this is scale multiplication, plus just this, because the other reduced to 1. And we can add these together, and you get this. Okay, this is where notation is a bit weird, and I'd like to correct this, or I'd like to correct up here. We used A twice. First, there's like some variable. Here it's just supposed to be like a placeholder, versus here was an example where we use some observation A. this is more like tier, such as any generic operator. And so when we refer to what a squared is down here, it's just a squared. And so you can think of this as just, rewriting it here would be better. This is just equal to a squared of psi. Does that make sense? This and this. Do we see? Perfect. Minus the square of the mean. Et voila. Mean of squares minus square of mean is equal to standard deviation squared, or variance. This is what we've had in like normal statistics. Okay? Perfect. Okay. Now that we're good, we have this point. Like say this is equal to, we're gonna not care about notation too much and just write this inside. Okay. Very important. So let's highlight the things that we're gonna use now. It's here. One as well here. Here. These are the things that are gonna pop up. Great. Now we move on to point 3, the commutator. For some background, without moving on to the claim yet, we're gonna say we want to see why a commutator is called a commutator. And well, take for example the case where the commutator is equal to 0. So not yet claim. If AB is equal to 0, what can you say about like AB and BA? Perfect. And so that's why it's like we say it's a commutator because it commutes. AB is equal to BA, BA is equal to AB. It commutes. And so we consider a case where it doesn't commute. Like, what's the next best thing that could happen? And that's how we define this. We want to find a scenario where the commutator like operation gives you just essentially a scalar in matrix form. And we're gonna show when this happens. In particular, when we have it in a relationship with our variances. Okay. Consider this second scenario, where our idealized commutator is, you can summarize it based on just multiplying by a coefficient essentially, or a scalar, multiplying by scalar complexes. If AB is equal to some k times I, then standard deviation, let's see how you put it, yep. Should I change notation? No, I did not mess up notation, okay. I might have put this before the A previously. Whether this is here or here doesn't matter. I'm just saying what's the standard deviation of your measurement A on the state psi multiplied by B is always greater than equal to the norm squared of your commutator. Oh, how would you call that, Miran? Like the K thing. Just call it some coefficient. Just like your commutator like scalar over 4. Yeah, we treat it as norm squared, just to make sure it's like positive, it's real.
When do you guys expect to like be free? Like 8:30?
No,
I
usually.
feel like we might be a bit short. You want me to do the proof?
No, I can do the proof. It's just, will we do anything after the proof? No, right?
No, it's just like explaining.
Right.
So
Maybe you
if
explain.
you guys are in a hurry, I can.
No, I got the proof.
Okay,
You in a hurry?
I'll do it.
You do the examples. I don't know how to like convince.
Don't do the example.
I don't know how to convince people. All right. We have an expression. The first thing you do when you think of an expression is if you can plug stuff into it. So we're gonna use.
It might be a better idea to be open this for open for the proof. Like,
I
copy
see.
anything and and then move it over. So because like looking at that direction.
I see. Oh wait, Miriam, we have the. You want to do actually? You might be faster. There's the middle steps. I pulled up here in case you need a class. Okay, Miriam's taking over. This stuff.
Okay.
You can do it faster.
So recall the variance formula.
Wait.
Recall the variance formula. This is probably not good enough. Okay. So we have sorry. Okay, so that's the formula we got previously. And can we see that? Yeah. Okay, so really this thing, we want to show that it's larger or equal than some number. So we try and write it out first. It's pretty long. It's going to equal to psi of a minus Okay, this is clear, right? This is really painful to actually calculate, right? So our life would be so much easier if we can just call this thing x and call this thing y, like the thing inside the square. Okay. So on the side, x equals a minus the mean of a times the identity. Right? We have these new operators. Equals b, dot, dot, dot. Okay. And then, yeah, so let's just write that. Psi x squared, psi y squared, psi. Okay. Now, we want to relate these x and y's with a and b's. So let's first check that these are nice enough. So the first claim is that x and y's are both self-adjoint. So x star is x. So do you see why this is true? You can also answer because you might forget. Yeah. Okay, so we know that A is self-adjoint, right? And then I is also self-adjoint. So morally, it should be like somewhat self-adjoint, right? So if we write A as some matrix, so here's the diagonals, and then here's a big chunk, here's a big chunk. And then this big chunk is going to be self-adjoint. It's going to be the complex conjugate of this chunk, right? Because when you take self-adjoint, you're flipping it, so it's transposing it, and then you're taking the complex conjugate. So the complex conjugate part goes down, and then you take it again, so it becomes a normal part, and then the other side, like yeah. So you see that, right? And then the diagonals, when you flip it, the diagonal still stays the same, and then when you complex conjugate it, it has to equal to itself. So the diagonals are real. Okay, so what happens if we subtract a number? So know that this thing is also real. Why is that? The average of a measurement of something, a physical measurement is always real, right? So the average must also be real, okay? If there's justice. If there's justice to our world, then it must be real. So you're subtracting something real off the diagonal. So you're subtracting something off, and it's still real. So this whole thing is still self-adjoint, right? Agree? So it makes sense. X is self-adjoint. This is the first claim. The second claim is the commutators are actually equal. To see this, it's probably just easier to expand everything. So do I have the space? I'll actually just pull the old board out. Okay, so we want to show that x equals a minus mean of a times I, y the same with b. So the commutator of x and y would be xy minus yx, right? So it's a minus mean of a, b minus mean of b, minus the other way around. Okay, so let's just expand this. A times b is just ab. And then these two, this is just a scalar. This is identity, so it just gives you b. So it's minus mean of a times b. These two terms, same thing, so it's just mean of b times a, right? And then the last two terms, you get a plus the two means with an I. And then the bottom line, you have a minus sign in front, and then it's the same thing. You just switch B and A around, right? The roles are switched. So here you have BA minus, this would be B average times A. And then you can see this would be a average times B, and then plus A average times B average, right? So this would be these two terms. Oh, wait, sorry. No, these two terms. These two terms, yes. And then these two terms. Okay, so these would cancel. You have a minus sign. So these cancel. And these two also cancel. Right. So what you're left with is just AB minus BA. So it's just a commutator of A and B, which is, we want it to be something like, sorry. No. Want it to be something like K times I, right? Okay, so what this is saying is basically doing this kind of operator transformation, you're still respecting the commutator. The commutator is invariant under this transformation. So that's a good sign. Okay, we're back. So the commutators are equal. I think 1, 2. Okay, so we can proceed. First, let's just move one of the x over because it's self-adjoint. So xi, xi, y psi, y psi. These are just norms. Like a vector dot product itself would just give you the norm. Not dot product, inner product. And then when you see this, you probably think of something, inequality. Exactly, yes. We want, let's see. Right? Schwartz, and a third Russian guy's name. I don't remember. I'm sorry. Okay. So this becomes larger or equal than the square of this thing, right? Well, I'm pretty sure there's like that. So the absolute value of that. And then, so you get absolute value of x psi, y psi squared. Okay. Know that this is an inner product, right? So inner products return you something in the field, which in our case is a complex number. So x psi, y psi is in the complex. What we can do is that there's something well known in the complex numbers. Just suppose this is a complex number, z. This is the imaginary part of z. This is the real part of z. From Pythagorean, you can see that the imaginary part must be smaller than the length of the vector itself. So you have the magnitude of z is larger or equal than the magnitude of imaginary z, right? And then a nice formula of writing imaginary would be why is it so wet? Z minus z bar over 2i. This would be the imaginary. Do you see why this is true, or have you seen it before? So, yeah, just a quick check for people who haven't seen it before. So z is a plus bi. Z bar would be I becomes negative I, so a minus bi. And then when you subtract them, a minus a would be 0. Bi minus bi, you get 2bi. And then 2bi you divide by 2i, so you get just b, which is imaginary of z. Okay, so great. This thing, a complex number, the magnitude squared would be smaller than the magnitude square of the imaginary part. So we write that in, 1 over 2i. Okay. What is the complex conjugate of an inner product? It would just be flipping it around, right? So take this out. We can write x and y in reverse. So y goes in front, x goes in back. Okay, so this thing is kind of neat. We can pull the 2i out, norm squared. So we get 1 over 4, right? And then what's inside is, we want to use some sort of bilinear property. So we want to make at least one of the entries the same. Let's just make the first one both psi, okay? So we move the x over. So it's psi xy psi. The order matters. And then here you move the y over, so y goes in front. So psi y x psi, whole thing norm squared. And then we can use bilinear property. 1 over, oh my god, what is this handwriting? 1 over 4 psi. We combine these two things, and because it's linear operators, so we can also pull them out. So it's just xy minus yx psi, which is our commutator, right? This is our commutator. xy. Yes. So no, I don't really want to. So what we have is would be larger or equal than 1 over 4. Let's do it in 2 lines. 1 over 4 absolute of psi commutator xy psi squared. Right? We have from our claim that if this is true, we can put that in. If the commutator is k times I, we can put that in. So it becomes just psi k, I times psi is just psi, so it's just k psi. K is a scalar, so we can pull it out of the inner product, right? Is a laptop like blocking, or we're good? And then finally, normalization. We assume our states are normalized. So we get our, oh, sorry, these should be equal signs. Finally, we get, this thing is just norm of k squared over 4. Done. Draw a little box. Yep. So now we have proven our claim. Let's move that over. The ones watching the recording can pause the video and think if this is true. And also, the board won't run away. Okay. We should write this somewhere. Draw some stars while people copying. That's how you spend your time. Also go drink some water. Stay hydrated.
Yeah. How do you?
You want to do the rest of it? The examples?
Yeah.
Or
I mean, the logic is dodgy.
Okay. Once you're done copying, just let me know. Just too close to my face. More stars. Okay. Perfect. Yes. Let's erase some things. So that's just a very long, boring proof, which taught you nothing about the physics. So we want to understand, what did we just do here? What does this mean? Let's look at an example. One of the most famous ones are, I'll just actually only say one that's famous. The commutator between your position measurement and your momentum measurement is IH bar times the identity, but no one cares about the identity. Yeah. So what does this tell us about our uncertainties or like variance? We can take the square root of these because square roots are monotonically increasing or something that preserves like the strengths. So you have the uncertainty in your position times your uncertainty in momentum must be larger or equal than norm of I h bar would just be h bar squared because it's purely imaginary. H bar over 2 because we took the square root. Okay. So there's some sort of lower bound in our uncertainty, which means we can't be absolutely certain. So let's just consider what if we have we can write uncertainty of P must be larger or equal than H bar over 2, 1 over uncertainty of psi of x, right?
Yeah, I just got it, bro.
You just understood?
Yeah, yeah.
Okay.
No, the explanations we don't wrote it down. There's a clear mathematical.
Yeah. Okay.
What's the last
No, you just divided by
Sigma
uncertainty.
psi of x.
You just divided.
Yeah. Sorry for handwriting. Everyone says that. Okay. So if you're more and more certain about your position, your uncertainty of your momentum must go up, right? And vice versa. You can divide uncertainty in P instead. And you get, if you're more and more certain about your momentum, you're less certain about your position. Okay, that sounds like something familiar from quantum propaganda. So this is called the Heisenberg's uncertainty principle. There's this joke of, wait, I'm not sure if I can remember. So Heisenberg, Einstein, and I think Ohms, they were driving and they were drunk.
Oh no, this is pure on Instagram.
Wait, I can't talk when I'm writing. Okay, so they're drunk, they're speeding, and then they got pulled over. And then the officer was like, you know you guys are speeding, right? And then Heisenberg says, I know exactly where I am now, so there's no way I know how fast I'm going. And then Einstein says, speed is relative, so you must be the slow one, so you think we were fast. And then Ohm just resists. Okay. Yeah, enough of bad jokes. Okay, so let's apply this to something we've seen before. Perhaps particle in a box, right? That's the only thing you guys have solved. Let's draw a box, which you have some wave function that's living in it. Let's just assume it's like some wave, doesn't matter. Right. So as we go more and more uncertain in our momentum, so suppose we have some momentum eigenstate, for example, and we know that eigenstates have a definite measurement because every single time we measure the momentum, it's going to give you the same eigenvalue, which is its momentum. It's going to give you the same momentum over and over again, which means the momentum would be absolutely certain. You're certain how fast you're moving, which means if this goes to 0, you're certain, I can't spell, happy face. Then this implies that your uncertainty in position must go to infinity, right? It goes like arbitrarily large, which means our wave doesn't look like this. It looks more like, because recall that the norm square of your psi would be your probability, like roughly your probability of finding your particle. So if your uncertainty of your wave goes like to infinity, you don't even know where your particle is. Your wave should look more like something that goes to infinity, right? Which means it's no longer contained in the box. You're uncertain because it could have like some probability of existing outside of the box, which is not possible because we confine our particle in the box. There's no way it's going outside. That's why we can't have any momentum eigenstates in this scenario, because that would violate the uncertainty principle. Does that make any sense? You're following? Good. And that's basically the punchline of today's whole thing, that we can't have momentum eigenstates inside a particle of the box. Some round of applause to Kevin, of course. He learned stuff in 2 days and was expected to present this. Yeah.
We didn't divide by them. We didn't take the square root.
I'm pretty sure I took the square root, and then I'm pretty sure you mentioned something about dividing, so I thought you understood. Anyways, yeah.
The math works out nice.
Okay. Questions, comments, complaints. That's what IUT says. Questions, comments, complaints. Complaints, yes,
well,
please.
if you do the opposite and you're really sure where your particle is in the box, like if you have zero certainty on, no, if you have absolute certainty on position, then you can go to infinite momentum.
Yes.
Are we okay with that?
Okay, so the question was, okay, by the way, it's a good idea if the speaker has a mic and someone underneath doesn't have the mic, and you should repeat the question. Okay, so the question is, if we have our position certainty go smaller and smaller, and our momentum uncertainty goes higher and higher, does that not cause a problem? Because we know from Einstein's relativity that you can't go faster than the speed of light. And how can you have like momentum that's going faster and faster, which would apply? Like either your mass goes to infinite or your speed goes to infinite, which makes no sense. So that is what they talk about, first lecture of quantum field theory. Keep these things. Put an X here and a P here. Okay, so you can imagine that your momentum inside the box. So what we want is our box goes smaller and smaller and smaller. So the side length, let's say, is L. As L goes to 0, then our uncertainty would be like roughly 0. What is that? So as this goes to 0, you have your momentum would be like roughly the uncertainty of your momentum, right? Because you're like 0 plus or minus your uncertainty in your momentum. So your momentum would be roughly h bar over 2L. Okay. And then as you go higher and higher, at a certain point, what happens is that, and your uncertainty in energy, just using classical formulas, which is wrong, would be like p squared over 2m, which you would get, what? H bar square over 8L square, right? At some point, this energy is going to go higher and higher, even though not necessarily just from this formula, because you need like relativistic corrections. So at some point, it's going to be larger or equal than like some 2mc squared. And then, which means that it has enough energy to create particles. And that's where the uncertainty That's where like the energy fluctuation or uncertainty goes. It starts creating particles instead of making your particle go faster and faster. So instead of your particle going faster and faster, you create 2 more particles. So now the box contains 3 particles. And 3 particles, they share the energy. So they don't go that fast. And as you shrink it smaller and smaller, you get more and more particles. So like 5, 7, 9, a whole bunch of them. So that's what happens when you have a box that goes smaller and smaller. Yeah. And then one thing to note is that if you have like 2 particles that jump out of nowhere, you probably want their mass to be the same. And then the charges are 1 is plus and 1 is minus because you have charge conservation. Yeah. This is called pair production, antiparticle and particle. Yeah. Questions? Any more?
How do we know that the commutator of x and p is I?
Oh, yeah, great question. Have you seen the operators themselves? Yes or no? Yes or no? You don't have to remember it. Yes or no?
No, we don't remember. We've seen it.
Okay, you've seen it, then that's good. Okay, so question was, why is xp IH bar? How do we even know this is true? Okay, so one thing to notice that in the x basis, whatever that means, you're basically looking at everything in terms of your position. So in the x basis, the x operator is just multiplication by x. And then the p operator, momentum, would be h bar over I. Or do you guys write things like this?
Yes.
Like, what's the notation?
Yeah, we've done
This, you understand this, right? This sounds familiar. Okay, great. And then we want to check the commutator. But these are operators. So what we want to do is test it on a test function. This is a pretty common idea. So you have xp, you apply it on some psi, some test function, test states. And then, so it's xp minus px psi. We write it out x. This is kind of confusing. Xp psi minus px psi. And then we put some brackets to remind us which ones carry out first. Okay. So this one we get h over I x partial psi. Agree? So we apply momentum's operator on psi, so we get this thing, and then we multiply by x, right? The other side is a bit more interesting. You have h bar I, and then you differentiate the entire thing, x psi, instead of just psi itself. So you have a product rule. Oh my god, I'm writing it so not horizontally. Anyways. So we have the product rule. So it would be the first one, so it's just psi. Differentiating x is just 1. Plus differentiating the second thing, so it's x partial psi partial x. Right. And then you can see that the first term and the third term cancels. Right? What you're left with is minus h bar over I. And then I has this very funny thing. It's 1 over I equals negative I. You can check this. So like, yeah. So you get IH bar psi, which is basically IH bar identity times psi. So we can conclude that since psi was arbitrary, we conclude that the operator is equal. So commutator equals psi. This thing is actually a pretty interesting fact, which says that the additive inverse equals to the multiplicative inverse, which is something cool in complex numbers. Yeah. Just a side note. More questions, more comments, more complaints. It's 8:30. We did start a bit late. So, yeah. If there's no more questions, I'll probably stop the recording, and if you want to write stuff.